So we have two sidebands carrying the same information. So one is redundant. All right.
So if you're trying to show something on screen, it's not showing enough.
You're not seeing the screen?
No, sir.
What? Seeing that now?
Yes, sir.
Okay. So we are saying that if we have our main signal and we have two sidebands, one of the sideband must be redundant because the two sidebands are carrying the same information. So the basic information is transmitted twice, once in each sideband. Therefore, there is absolutely no reason to transmit both sidebands in order to convey the information. Right? So if you have two modes of transportation carrying the same information, yeah, you protect yourself in case one broke down or something happened. But there is, if both of them get there at the same time with the same information, one of them is redundant. That's all this is saying. So we can suppress one of the sideband. So if you suppress one of the sideband, the resulting signal is a single sideband, commonly referred to as single sideband suppressed carrier signal. So here is your spectrum of your baseband signal. This is your baseband signal. This is what you want to transmit. So this is your single sideband, your double sideband. Both of them carry the same information. So this is your modulated signal in a double sideband format. So if you notice what we do here, we're going to take off this portion and this portion. so we don't totally kill one of the band. We're just using half of it. Right? And I want you to pay attention. The of the picture. All right. So that when you get into the mathematics, it makes sense. You know, because it's beyond me. Some of the comments I see in the chat groups when people show up halfway through the class, they miss the picture and they say, they don't learn anything. Right? But I learned to just ignore that. So look at this. Look again. This is your spectrum of baseband signal. This is what you want to transmit. Right? So this is your double sideband modulation. In other words, you're transmitting the same signal in two bands. Okay. So one is kind of waste. So you want to transmit it in one band, but you don't want to kill the other band, in layman terms. So this is what you do. Okay. Or that. So let's go to the mathematics now. So this is your time domain description of your single sideband signal. So you're gonna use your Fourier transform, convert this time domain signal to frequency domain. And of course, you are quite up to speed on your Fourier transform. So convert this time domain signal to this. Who can do that? Nobody can tell me, say, no, 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 Fourier transform. You know? Because we have about 2 courses to teach you that, you know, brother and sister.
Yes, sir.
Yeah. So, can you make your way from here to here?
Sir, and I saw clear in my head again, sir.
Well, you need to just review your thing. It's part of this. In a way, from the time domain to the frequency domain, this becomes this. So, I'm going to look at, we're going to look at the figure and come back to this. Yes, this is the figure they're referring to. So, for f greater than 0, S of f equals half j over 2 ACMJ, m of t. For j equals 0, 0. Or for f equals 0, 0. And for f less than 0 is half ACM of f. Right? Which gives you this. Right? Yeah.
Is that half or j over 2, that's sir?
Here,
Yeah, I can't exactly say what.
yeah, it's supposed to be f.
All right, sir.
Okay. So we that was the spectrum of your single sideband wave. But let's play some games with it. So we're gonna shift it to the right, IFC. So if you shift this to the right, if you keep shifting this, you're gonna get it back together, right? So you shift it until you get it back together. In other words, the single sideband, you take what would have been the double sideband and you only transmit half from one sideband and half from the other sideband to your destination. And then you recombine them. Let's go back to the picture. Here is your baseband. This would be your double sideband. It's a one of the band redundant, but you don't want to kill. In other words, you could use either this or this band to transmit the signal. In the double sideband configuration, because they both carry the same information. But you don't want to kill this one and you don't want to kill this one. So you just take off this and take off this. So you have less, you only have half this side to transmit over here and this side to transmit over here. So this is what you end up with. Right? Or this. This is the Fourier transform to deal with this. This is your time signal. This is your transform signal in the frequency domain. So here you are. So when you reach your destination now, you have to bring it back together. And there you are. So you're back to this. Equation. All right, I'm going to restart this thing. I guess there are no questions because I'm sure we don't understand the math.
Sorry, it looks similar to the one we were doing before, double sideband, but well, you have halves now, so the constant we would have AC into
Hello?
hello, sir.
You know, I was here talking to myself and no one was responding. So that's why I had to go back and check and see that I was muted.
Okay.
Sorry about that. So
Sorry,
the
not
question,
seeing the screen. Oh.
sorry about that. You seeing it now?
Yes, sir.
Yes, sir.
Okay. So the question I had, right, was what I have is why single sideband modulation? Why do we want to do single sideband modulation?
Because it saves power, sorry.
Yeah. All right. Because we are doing the same thing in double sideband modulation, we are doubling our effort, right? We have
Yes, sir.
our signal. We want to move from the generator or the transmitter to some receiver, right? So we do the double sideband modulation because we want to have a backup. Right? But the reality is that one of them is redundant. So we come up with a unique way of doing the single sideband. But we don't kill one of the band to do the single sideband. We use the two band the same, but we only transmit half of the information in one and the other half in the other. And then when we get to our destination, we combine them. Okay. So that's the basics of the single sideband modulation. Of course, there are different techniques. We are going to look at one of the techniques called the frequency discrimination method. So let's look at this cartoon. This is your information. This is your carrier. And this is your modulator. You put it through your filter to get your single sideband wave. Exactly what we did with the when we did in modulation in the general terms. So the only adjustment we have here is your filter. See if you're with me. You remember at the beginning of our study on modulation, we said we have our signal, our carrier frequency, we combine it, we send it to a filter, and then we get out here where we demodulate, right?
Yes, sir.
So this is exactly the same thing we're gonna do with the single sideband modulation. The only difference here is your filter is gonna tell your modulator that, listen, I'm only gonna transmit that half of your modulation signal below F equals 0 and that half below above F equals 0. So it's not a magic. Right? This is the, I look at it in in the frequency and time domain, because this is your information signal. This is your carrier frequency. Right? You get a voltage go through this bandpass filter. Right? And now this signal, so this signal, you get a signal out here of your bandpass filter. Right? And here now, you recombine with the second modulator, and you send it back to a filter to get back your signal in the time domain. So this this is 1, 2. Our problem as engineer is to design this modulator, this filter, or these modulators and these filters. But what we are doing, and when we look at this, is the technician aspect of the work. This very competent technician that call himself engineer and claim he know more than us. Right? You don't deal with the Fourier transform in these things. And the representation of signal to go through the components to get from here to here. You just connect up these, you know, and you'll get your signal straight from Ukraine. You with me?
Yeah.
So this one up here, we call the frequency discrimination method. So let's look at like I tell you, there are different techniques that we do it. So let's look at the phase discrimination method. All right. So this is what the signal is doing. This is your signal coming in. It's the same signal here, but we're gonna shift the phase of this. All right. So when we shift the phase of this now, let's follow this one. This is the same thing as above. Same signal is gonna go here. So this signal is the outer phase. All right. Now, this signal here in this product modulator, we're gonna send the same signal to the summer out here. We're gonna also send the same signal to a 90 degrees. So we're gonna know by how much we shift this here. So we shift this phase by a known amount and we shift this phase. Then we do the modulation. All right. Then when we go back here, we sum it. So we get a single sideband which is shifted by a known phase. This case 90. See if that makes sense to you. You see, when you're using a phone and you can rotate the signal and all of that. You know, that's what I'm talking about, man.
Okay, like yes, sir.
Yeah, man, it's modulation at work, you know, phase shifting and all of that.
Okay. Yeah.
It just didn't happen just like that. And then you have the phase discrimination method, which is that. Let's see what this is.
Sir, like when you have signal drop, sir. Like when you have a poor signal or something like that.
For what?
Because you said the phase discrimination, something like when your phone won't pick up or something like that. What do you mean like when you rotate it, like you turn it?
No, you know, you see sometimes remember like you're watching something on a phone and you just turn the phone 90 degrees and the picture turn, right?
Okay, yes, sir.
So you're looking at it. You get a longer picture, so to speak. Right? So that I'm just saying that is like that's an example of phase shifting at play.
Okay.
But like a phase discrimination now is exactly what you said. Discrimination, you eliminate a certain orientation from coming through. This one, you can go through this one. The weaver method, you can go through that on your own. So let's look at a comparison of the different method. Yeah. So this is now if you're gonna design a system, okay? If you're gonna design a transmission system, right? Which one of the single sideband modulation method would be most appropriate? Yeah. So this is basically, if you're out in the field, you would have like a chart like this based on the back of your notebook. Until you get old like me, you know it by heart. Okay. So like I said, you're at the end now where you're gonna use the signal. So let us spend a little time on this block diagram. You get your signal loud and clear from the Kremlin to the White House. Okay. Noon time. So how we are going to get this information to Mr. Biden now? We have to convert it back to the time domain, right? And all you have to do is So this is demodulation. So demodulation is modulation backward, you know, so?
Yes, sir.
So you send a signal through a demodulator. Right? And when we were coming up the line, we filter it one way, so we have to filter it the other way. So demodulation is basically just modulation in reverse. In other words, if you can design a modulator, you can design a demodulator. So there you go. You have your two single sidebands. You recombine them. Before I go on to the equations, let me this is a lab that they do in New Jersey. You guys, if you use Similinks before, right?
No, sir.
Remember, you use Similinks.
No, sir.
I don't. I really don't. Still, I don't think you have to have any prior knowledge. It's pretty straightforward. I'm gonna send it. Let's see if we can do this one to complete our work on modulation. It's pretty comprehensive. So you said no one really got to complete that lab that we said last week.
No, sir. I think the closest somebody probably got was, I think there was a registration page, but then we never hear nothing else about that.
You never asked me to register. Well, anyway, this one, as soon as at the end of the class, I'll just send this one to you. Let's see if we can do this one. Let's go back to it. All right, because here it is. It's all just simulation. That's just an example. So it's just showing you the different modulation signal and what is really happening, and explain as you go through. You know. Very detailed. Double click on the signal generator.
Sorry, if you're trying to show us, we don't see it, we're still up on the PowerPoint screen.
Still up on the PowerPoint screen. Oh, shoot. So I have to go. You seeing it now?
No, sir.
I'm gonna restart and come back. See what's going on. You get me? You guys are with me?
Yes, sir.
So I'm saying, like, once you set this up, it's pretty straightforward. Double click on the signal generator and you set your frequency and you make your adjustment. So essentially, it's like you would be building this circuit in the lab, but you're just building it in the simulator, right? And it will show you when you make the adjustment what your modulated signal looks like. Yeah, you will see things like this. I think you will enjoy this.
Looks interesting. So
I when I was going through it this morning, okay, to call it what it is, I was just learning it at the same time. And I found it very, 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 very interesting. So I wanted us to hear like this one, like here. You know. So it give you the specific lab task. But nobody look on it and just say, this is too difficult and don't do it.
So this is MATLAB. This here was something.
Hmm?
Yeah, I just saw in the references is you use MATLAB to, but you have to install that service pack or something like that.
I hope they don't ask you for no money for install.
Oh, so I think they give us free at UTech now, so with the student email.
Yeah. Mm. So I want you to go through that. Mm. Yeah, man. You back with me here?
Still seeing the log.
Okay. You're back on the PowerPoint?
Yes, sir.
Okay. So here's the part that none of us like now. When we were going through the picture and showing you that, it was cool. So here are the equations now. So you tell me if you make any sense out of any of that.
Not really following, sir. I see.
God is the creator. God is the creator. But I can't look at your diagram of here. All the way back to I guess if you couldn't do this, that's gonna be a problem the same. But we looked at okay.
Sir, I see like where you have the carrier signal.
And your product manipulation.
Yes, sir. They would
Mm.
you would have MT be the message,
This signal.
MT would be multiplied by AC because 2 pi FC.
Right here. Mhm. So if we go back to those, look like complex equation, which they're really not. So this is. When we send the signal through that block diagram, well, this is the signal that we combine, and this is the result of your transform.
Sir, is A prime C the filtering function?
Exactly.
Oh, okay.
So this is what you get at your output.
So I see there is some trigonometry in the equation, sir. The first equation. In order to move on to the next.
You mean from here, from you write this straight from the block diagram,
Oh,
and you
okay. Okay.
just do your transform.
Sir, is there a benefit of using the single sideband versus double sideband?
Yeah, you save, like I said, with double sideband, you're transmitting the same signal twice.
Oh, okay, sir. But the single sideband would be a more complex circuit then. Yeah, at least you would have more parts.
For the single sideband,
Yes, sir.
yeah, because you have to have additional filter. But once designed, it is basically transparent, and you save on your transmission.
Okay. Sure.
So this is just going to show you in your transmission the effects of various errors. Okay. This last one in modulation, I really don't want to do it, but I want to go through it just quickly so you are aware. You know the double sideband and you know the single sideband. This is kind of broader. The vestigial sideband. So your baseband signal remain the same, right? So if you see the vestigial sideband is neither it's not a double sideband, a single sideband. It's warped. So this is what you have to do. The process is the same. You have your message, you have your carrier, you have your product modulator, you get your modulation wave. So again, this is your filter doing the work. So it's just a different kind of signal, which is gonna use a different kind of filter. And once you know how to design filter, the story is the same. So let's look at the pictures.
So, sir, you can like warp it to, like you can change the wavelength or so to your choosing.
You mean
Like if
not?
you
Go ahead.
like say one part of the signal has more energy than another part, it can like, or that just depends on the input. So if one part of the
No,
signal has a bigger
you mean like here?
yeah, yes sir, and it is uneven, like you would
Right.
um,
So this is what our filter gonna do now. This is your vestigial signal. What we're gonna use our carrier signal for the single sideband to make sure it fit like this. Because we can't just allow it to be anything it want to be. We have to restrain it. So we have to fit it on top of the carrier signal in our modulation process. Right? So whatever your signal is here, we're gonna have to set our carrier signal to fit it on top of it, so that we can work with it. So I guess this will answer your question. And that's what you get out through your filter. Like I say, you fit it into the parameters of your carrier signal. So this is the envelope. And this is a table that show you a comparison of the different modulation technique which suit what best. Single sideband is less power. Yeah. Single sideband radio communication. USB television.
still don't fully understand what the vestigial sideband is, sir. Maybe it's a new term or something. So not sure.
We're vestigial in English.
Um,
Take us along to Google it.
It says forming a very small remnant of something that was once greater or more noticeable. So I guess it's
Mhm. So is that the signal, for lack of a better term, the signal is going all over the place. So you use the carrier frequency to, or the carrier signal to restrain it. But just to the point where at the end you can still recover it. So it's like you capture the DNA. It's unique to that signal. Look at the block diagrams. Anyway, we'll be more comfortable. We're not gonna deal with the Hilbert transform. Be good for you to know what. Can't do everything. So that's a lot of information for you to go hang down your head and delve into. And I'm going to hold it to just doing that. So next week we'll start a new topic. And the other week we'll do an easy test on modulation. All right.
Okay, sir.